Los Alamos National Laboratory was established during World War II as part of the Manhattan Project. The Manhattan Project was a highly secretive research and development undertaking during World War II. The project's urgency stemmed from the global conflict and the perceived threat of enemy scientific advancements. Secrecy was paramount to the Manhattan Project, with information tightly controlled and access strictly limited. The Manhattan Project was initiated with the objective of developing the atomic bomb during World War II. The project presented significant scientific challenges in nuclear physics and engineering. Expert commentary provides historical context and insights into the project's complexities. The creation of the atomic bomb involved multidisciplinary collaboration across various scientific fields. Archival footage reveals the scale and intensity of the research and development efforts. Nuclear fission requires complex calculations for understanding and control. Manual calculation methods proved insufficient for managing the intricacies of nuclear fission. Simulation provides a means to visualize and analyze the chain reaction process in nuclear fission. Controlling nuclear fission requires precise monitoring of neutron flux and energy release. Simulations allow for the optimization of reactor design and fuel management strategies. Advanced simulations are essential for predicting and mitigating potential risks associated with nuclear fission. ENIAC, the Electronic Numerical Integrator and Computer, was among the first electronic general-purpose computers. ENIAC's design incorporated numerous vacuum tubes, resistors, and capacitors. Programming ENIAC involved manually setting switches and plugging cables. ENIAC occupied a large room due to its extensive hardware. ENIAC was designed to calculate ballistic firing tables for the U.S. Army. ENIAC's innovative design paved the way for modern computing. ENIAC was initially designed to calculate ballistic trajectories for the U.S. Army during World War II. Ballistic trajectory calculations involved complex differential equations that were time-consuming to solve manually. ENIAC significantly reduced the calculation time for a single trajectory from days to minutes. The machine's ability to rapidly compute complex equations made it invaluable for military applications. After the war, ENIAC's capabilities were extended to nuclear physics and other scientific fields. ENIAC's success in ballistics paved the way for its broader use in scientific research and development. ENIAC was adapted to perform calculations for the Manhattan Project. Modifications were made to ENIAC's hardware to suit the specific needs of nuclear calculations. Programming techniques were developed to optimize ENIAC for complex physics simulations. The adaptation of ENIAC involved both hardware changes and software innovations. These adaptations enabled ENIAC to efficiently handle the computational demands of nuclear research. The ENIAC simulation calculated the critical mass of fissile materials. Determining critical mass was essential for designing an effective atomic bomb. Critical mass refers to the minimum amount of fissile material needed to sustain a nuclear chain reaction. ENIAC's calculations provided crucial data for optimizing bomb efficiency and yield. The simulation allowed scientists to explore different fissile materials and configurations without physical experimentation. The implosion method relies on precisely compressing a subcritical mass of fissile material to achieve supercriticality. High explosives are detonated simultaneously to create a uniform, inward направленный shock wave. Achieving a symmetrical implosion requires extreme precision in the design and manufacturing of the explosive lenses. ENIAC, one of the earliest computers, was used to perform the complex calculations necessary for the implosion design. The precise timing and uniformity of the shock wave are critical for successful compression and subsequent nuclear fission. The implosion method allows for the use of plutonium, which is more readily available than highly enriched uranium. Verification of ENIAC's calculations was crucial for ensuring accuracy in the bomb's design. Scientists and engineers meticulously reviewed ENIAC's outputs to validate computational integrity. The accuracy of ENIAC's calculations was paramount for the success and reliability of the bomb's design. Rigorous verification processes were implemented to minimize errors and ensure the validity of ENIAC's results. The Trinity test marked the first successful detonation of a nuclear weapon. This event represented the culmination of the Manhattan Project's extensive research and development efforts. The test demonstrated the destructive potential of nuclear fission. Historical footage documents the immediate aftermath of the explosion, revealing the landscape's transformation. The Trinity test provided critical data for understanding nuclear weapon effects. The success of the Trinity test had profound implications for global politics and military strategy. The Little Boy bomb utilized a gun-type fission weapon design. Fat Man employed an implosion-type design for nuclear fission. ENIAC's calculations were crucial for determining the implosion lens design in Fat Man. The designs of both bombs aimed to achieve supercriticality for a rapid and powerful nuclear chain reaction. The atomic bombing of Hiroshima caused widespread destruction. The impact leveled buildings across a wide radius from the hypocenter. The scale of the devastation highlights the destructive power of nuclear weapons. The bombing resulted in a near-total loss of infrastructure. The event underscores the catastrophic consequences of nuclear warfare. The aftermath reveals the fragility of urban centers in the face of extreme force. The atomic bombing of Nagasaki caused widespread destruction and devastation. The impact of the bombing resulted in immense loss of life and long-term health consequences. The bombing had a profound and lasting impact on the city's infrastructure and environment. The events in Nagasaki serve as a stark reminder of the destructive power of nuclear weapons. The bombings resulted in immediate loss of life and long-term geopolitical consequences. Expert commentary analyzes the multifaceted impacts of the bombings. Geopolitical consequences include shifts in power dynamics and altered international relations. Long-term impacts encompass economic, social, and environmental repercussions. The development and use of nuclear weapons raise significant ethical concerns. Scientists bear a responsibility to consider the ethical implications of their research. Policymakers must grapple with the moral dimensions of nuclear weapons policy. Open discussions are essential for navigating the complex ethical landscape surrounding nuclear weapons. ENIAC's innovations laid the foundation for modern computing technology. The transition from ENIAC to modern computers represents a significant leap in processing power and miniaturization. Modern technology continues to evolve. Building upon the fundamental principles established by ENIAC, the societal impact of technology is an ongoing discussion, influenced by ENIAC's initial applications. ENIAC's legacy extends to various fields, including science, engineering, and data analysis. The debate about technology's role in society remains relevant, shaping future innovations and policies.